Okay, so today we are going to talk about section 3-6, which is graphing the parent function for the square root and the parent function for the cube root and all their transformations. So this is really going to be your first introduction to a parent function and how you transform them. From here on out, we're going to continue to add new functions to our group of parent functions, but the transformations essentially stay the same. So for the first part, what is the square root parent function? So the square root parent function is f of x. Actually, I'm just going to use y. It'll be easier. So y is equal to the square root of x. So let's go ahead and graph this parent function and see what we might get. So at first we're going to use a table of values. So I'm going to have an XY table. And you want to ask yourself, what is the smallest number that I can put in for x? Because x is my input and y is my output. So can I take the square root of a negative value? No. So I can't put any negative values here. So my domain underneath the square root is restricted. Can I take the square root of 0? Yes, a lot of students think that you can't, but you can. So I can take the square root of 0, and the square root of 0 is 0. So that's 1 point. Then I want to choose my points wisely. I only want to choose values to go under here that are perfect squares. So my next value after 0 is 1, and that is a perfect square. So the square root of 1 is, and I guess I'll put on here what I'm actually doing, the square root of 0 equals 0. And we input 0 into here. And then for this one, we're going to take the square root of 1. And the square root of 1 is 1. The next number after 1 is 2. If I put 2 into the square root, it's not a perfect square, so I can't take it. Same thing with 3. However, 4 is a perfect square. So that's the next number I choose to put in. So the square root of 4 is equal to 2. The next square root after 4, it's not 5 or 6 or 7 or even 8, it's 9. And that's going to be about as far on the x-axis as we can go. So that'll be the last point that we choose. And the square root of 9 is 3. So I'm going to plot these ordered pairs. So I'm going to plot 0, 0, and then 1, 1. And then 4, 2, and you can see at this point we have a curve starting, and then 9, 3. So my points are a little off with my cursor that I'm using, but yeah, you get the idea. So then I'm going to connect these points into a curve. If you connect them with a straight line, you'll be wrong. So that is the graph of the square root of x. So let's talk about a couple of things. Square root functions have an endpoint. We start here and it continues infinitely to the right and up. So we really need to know what that endpoint is. It's a vitally important part of our graph. And whenever we translate the graph up, down, right, or left, we need to know where that endpoint is so we know where to start. So for our purposes here, our endpoint is 0, 0, the origin. And then we're going to look at the domain. So our domain, if we look from left to right, because that's the direction of the x-axis, the smallest x value that we come to is right here. And the x value here is 0. And so our domain starts at 0. And because 0 is part of our answer set, it's a value that we can put in for x. We have 0 here. Since it's part of our domain, we're going to include it, and that means that we need to have brackets here. And then how far to the right can we go? In other words, is there any number too big that I can't take the square root of? No. So our domain continues to go to the right infinitely. So that means that our domain goes from 0 to infinity. Then our range, remember, goes from low to high. So the lowest value I come to, again, is at this endpoint, and the y value of that endpoint is, again, 0. So my range is going to start at 0, and because 0 is part of our range, we're going to have a bracket. And then this graph keeps going up and to the right and up forever. So the domain and range in this particular case are identical. So let's look at the cube root function. So the cube root function is y equals the cube root of x. So when we choose values for x, we need to choose values that are perfect cubes. So I'm going to start off with my xy table. And we're going to look at the x-axis here because we need to choose perfect cubes so we can take the cube root that are going to fit on my graph here. So my graph goes out to 10. Well, 10 is not a perfect cube. So I'm not going to start I'm at negative 10. It's not a perfect cube. But the next number here is negative 9. Negative 9 is also not a perfect cube. But negative 8 is, because negative 2 times negative 2 times negative 2 gives us negative 8. So I'm going to start on my graph with negative 8. And I'm going to keep moving all the way to the right and include all of my perfect cubes. So the next number after negative 8 is negative 7. That's a no. Negative 6, no. Negative 5, no. Negative 4, no. Negative 3, no. Negative 2, no. But negative 1 is a perfect cube. So then we're going to put in negative 1. And then 0 is the next number, and you can take any root of 0 you want to, just like you can take any root of 1 as well. So 1 is another perfect cube, and then going to the right, of course, would be 8, and that's all of our perfect cubes. So I'm going to plug these numbers in. Okay, so I'm going to substitute in a negative 8 here, a negative 1 here, 0, 1, and 8. And so then the values that I get, we already talked about that the cube root of negative 8 is negative 2. So that's my y value. When I input into x a negative 8, out pops a negative 2. So my y value is negative 2. So then we're going to input negative 1. So negative 1 times negative 1 times negative 1 is negative 1. So the cube root must be negative 1. Cube root of 0 is 0. Cube root of positive 1 is a positive 1. And cube root of positive 8 is a positive 2. So those are 5 ordered pairs that we're going to plot. So negative 8, negative 2 would be about here. Make that bigger. And then negative 1 is going to be here. And 0, 0, and 1, 1, and then 8, 2. Whoops, my points are a little sloppy, so sorry. You try working with a stylus. All right, so you're going to put a curve through this. It's kind of a sideways S curve going through there. So that's the square root function. It doesn't have a start and it doesn't have an end. It starts here at negative infinity and keeps going up a little bit and then to positive infinity. So your domain is going to go, the leftmost x value is negative infinity, the rightmost x value is positive infinity, because the graph keeps going forever from left to right. So let's write that in here. So our domain is negative infinity to positive infinity. Our range, the lowest range value, so if this is going to the left, it's also going down, 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 down forever. So our lowest range value is also negative infinity. Our largest range value, as we go up, this is going to the right, but it's going up and up and up and up and up forever. So the largest range value is also positive infinity. Then we have this thing called a turning point. Where's this graph turning? If you look here, I'm going here, and then I go into a curve, and then boom, I'm going up in this direction. This right here is called the turning point. So I'm going to turn that into a dark black point. So on the parent function, 0, 0 is our turning point. So on these graphs, you typically have a turning point or an endpoint. All right, so let's look at transformations. We're going to start with, and it doesn't matter whether we have a square root or a cube root. So as you can see here, we have an nth root. So it doesn't matter what root we have. You could have something outside of the root being multiplied. And then here's our input value. So the things that don't change here, and instead of x, we have, or instead of y, we have f of x. So here's our x, and here's our y. Remember, that's no different than having a y, right? So here's what's changed on our parent function. So we could have something multiplied outside the function. We could have something being added or subtracted inside the function. I know it says minus h. We'll get to that in a minute. But it could be, x plus 2, x minus 2 inside this function. So if something is being added or subtracted inside the function, it's affecting your input or your x value, because you have to take your x value and add or subtract this to it. It doesn't technically affect the answer. Then you could have something being added or subtracted outside the function being the root. And if we have something being added or subtracted outside the function, it's actually affecting our answer, because this is already the function. Remember, if we were to isolate this radical, you would add or subtract this k to both sides, which affects that y value. So if, and let me move this down a smidgy, there we go. So we have a couple of questions. H is the blank shift. So H, because it's affecting the x, and x goes right and left is a horizontal shift. Now, I don't typically make you say the word horizontal with going up, down, right, and left. All I expect is up, down, right, and left. But for our notes, we're going to call this the horizontal, because right and left is horizontal. Now, weird but true, and I'll prove it to you in a minute when we graph them. If h is negative, so it might look like x minus 2, you would think if it's going right or left that it should go left, and it actually goes the opposite direction of what you think. So if this is a minus here, it's going to actually go to the right. So a minus shifts the graph to the right, however many units. But if this is a negative, or a positive, x plus 2, it's going to go in the opposite direction, because on the x-axis, a positive will go to the right, but we're really going to the left because that's the opposite direction of a positive. So a positive is going to shift our graph to the left. Then k is outside the function. So we're outside the function is going to affect our y value, and so y goes up and down. So whatever this value turns out to be, if you add k to it, it's going to increase the answer and make you go up. If you subtract k, it's going to decrease the answer and make you go down. So k goes up and down, which is a vertical direction. So k is the vertical shift. And is exactly as you think it would be. So if the k is positive, you're going to go up. If the k is negative, you're going to go down. So positive shifts up, negative shifts down. So you might need to put those on flashcards and study them. This is a study issue for you. All right, so then the other thing we need to talk about is this value out in front. If this value out in front is positive, then the graph is just going to remain like a normal parent function. So in other words, the square root function goes like this. If a is positive, that graph is going to look like it's going like this. But if the a is negative, it is going to reflect the graph across the x-axis. And so if you look up here, if I reflected this graph across the x-axis, it would get reflected here. That's its mirror image. So that's what a reflection would look like. And that's if A is negative. So I'm going to erase that because I really don't want that there. And then also, what would the cubic function look like, or the cube root function look like reflected? Well, this right part would reflect like this, and this left part would reflect like this. So it just flips. So this part flips over the x-axis and goes up here. This part flips over the x-axis and goes down here. I'm going to take that away. Undo. Undo. Is it not undoing it? We'll see. Nope. There it goes. All right, good. Good, good. Let me make sure that this went away up there. Yep, okay, so we're all good. So back to our note. So right here, our endpoint or turning point, you can figure out your endpoint or your turning point by looking at H and K. So it's going to be H. Notice I didn't write positive H. So it's going to be H, comma, K. That's how you're going to find your endpoint or your turning point. So notice here it says minus H. So whatever H is, you're going to take the opposite of it, and that becomes the H of your endpoint or your turning point. So if you have x minus 2, your H value, which is going to be your x value of your turning point, if it's x minus 2, would be a positive 2. If it were an x plus 2, you'd take the opposite and you'd put a minus 2 here. Your k, however, notice that k is a positive here and it's a positive here. So whatever this k value is, that's what goes here. So if it's a plus 2 on the outside, you put a plus 2 here. Minus 2 on the outside, you'd put a minus 2 here. All right, so then back to where a is negative. So if a is negative, let's go ahead and write this in here. All right, if a is negative, the function is reflected. So that's the transformation across the x-axis. And the reason why it's reflected across the x-axis is if this is negative, it's outside the function, it's affecting the answer. So if the answer was positive, a negative will make it negative. If the answer was negative, a negative will make it positive. And so it will flip up and down. All right, then the other thing that you have to look at with A right here is it creates this vertical stretch or a shrink. If A is, and we're looking at the absolute value of A, not whether it's positive or negative, so you have to consider the absolute value of A. If A is a number greater than 1, like 1.1, 1.2, 2, 3, 4, 5, 6, right? So if A is a number greater than 1, you will have, let me choose, I don't know, we'll do blue. You will have a vertical stretch. And what that's going to do is going to stretch your graph up and down and pull it closer to the y-axis. If A right here is a value between 0 and 1, so that would be a fraction less than 1, so like 1/2, 2/3, 3/7, something between 0 and 1, and again, we're looking at the absolute value, you will have a vertical shrink. And that means that the graph is going to be pushed down to the x-axis. So a vertical shrink is going to make something closer to the x-axis, and a vertical stretch is going to pull it closer to the y-axis. Okay. Then let's go ahead and look at some equations and use what we learned above and compare those transformations. So the first thing I want to note here is endpoint or turning point. So as you look at this equation, I don't even have to graph it. I know that this is going to be my h and this is going to be my k. Because it's a square root, I know that I have an endpoint. So I'm going to call it EP. So this is my h and this is my k. So my EP, remember my H is going to be the opposite of what I see here. So because I see a -7, I'm going to put a +7, but the same as what I see here. So a 2. So my endpoint is 7, 2. Then I'm going to describe my transformation. So I only see 2 things happening here. There's nothing out in front. So I don't have a reflection and I don't have a vertical stretch or a shrink. So inside the function, it looks like I should be going left 7, but remember inside the function is the opposite of what we think it's going to be. So instead of left 7, we're going to be going right 7. And then outside the function is a +2. Outside the function affects our y, so that's up and down, and it's exactly what we think it is. So since it's a +2, we're going to go up 2. All right, so then we come to a cube root. Because it's a cube root, we don't have an endpoint, we have a turning point. So this time, I'm going to call this the turning point. So notice, and you have to look really carefully, there is nothing inside the function. This -1 is happening outside the function. So inside the function, if nothing is being added or subtracted to x, remember that nothing is 0. So that means my h is 0, and then my k is outside the function here. That's a -1, and we use exactly what we see for k. So I know my turning point is going to occur at 0, -1. So then let's describe the transformation. So right now there is no right or left shift. So because there isn't one, we don't have to talk about it. But this -1 creates a shift. It's outside the function, so that's up or down. Because it's negative, it's going to go down 1. The other transformation is the fact that you have a 4 outside the parent function. Remember, when you have a 4 out here, if a, right here, the absolute value of a is greater than 1, which it is, we have a vertical stretch. So vertical, and you can just put vert, but I need to see the whole word stretch. And you have to say of what? Of 4. Okay? Each of these transformations, except for the reflection, you have to have an amount. All right, so then I want you to try 3 and 4 based upon what we talked about up there. So pause the video, try those, and then we'll talk about them. Find the endpoint or the turning point as well. Okay, so for this one, because it's a cube root, we have a turning point. So the turning point is going to be inside the function is a -3. Well, it's a +3, but I'm going to take the opposite of that, which means that my h is a -3. Because there is nothing happening, nothing being added or subtracted outside the function, my k must be a 0. So I know my turning point is -3, 0. Then outside the, whoops, I did not want that. Outside the function is a negative. So that means that we have a reflection, and you have to say what it's reflecting over. So it's a reflection over, I'll put a little mark there, over the x-axis. Okay, and then the final thing on this one is we have a +3 on the inside. So inside is right, left, and it's the opposite of what we see. So the opposite of a +3 would be going left 3. All right, and then over here on this one, this 1/2, the absolute value of 1/2 is less than, is between 1 and 0. So because it's between 1 and 0, I know that we have a vertical shrink. Couldn't think of the word there for a minute. So you have a vertical shrink of, and you have to give me the value, 1/2. And then inside the function, we have a -2. So inside is right, left, and it's the opposite of what we think. So it should be right 2. And then we have this -6 outside the function, and outside the function is exactly what we think it is. Outside effects are up and down, and so this would be down 6. And the one thing that we haven't talked about is, do we have an endpoint or a turning point? Because this is a square root, we have an endpoint. So our endpoint is going to be the opposite of negative 2, which is 2, and the same as negative 6. So 2, negative 6. All right, let's look at the back. So on this page, we're continuing to look at our transformations, but this time you are given the transformations and you have to write the function. So a couple things that are important. So I'll do the first one with you, is the fact that it says it's a square root parent function. So the first thing that I'm going to do is I'm going to write, and you can write f of x or y, it doesn't matter to me, y equals. And I'm going to write this cube root. Oh, square root, my bad. Good thing I paid attention. It's a square, good thing I highlighted it. So it's a square root, sorry, not a cube root. All right, and then I have an x here. So then we have to decide what's going on. So it's reflected across the x-axis. So the fact that we are reflecting something across the x-axis means that there must be a negative out in front of that square root. Now, I don't know if there's a number here yet. We'll keep reading. So in fact, I'm going to underline that in red and color code it to my values here. Then shifted 7 units left. So 7 units left is a right-left direction is in the x direction. So 7 units left. Left is normally negative, but inside the function, we do the opposite. So it's a positive 7. And then 1 unit down. So 1 unit down is an up-down movement, which is outside the function, and it's exactly what we think it should be. So it should be a -1. So because we weren't told that we had a vertical stretch or shrink, there's no number here other than 1. So we can just keep this as a negative. And this is our equation. All right, so you pause the video and I want you to try to figure out what the equation is for this one, knowing that it's a cube root function. So pause and go. All right, so I have a cube root function. So I've got y equals, and then I have a cube root. And then this one is interesting because it says it has a turning point, which makes sense, at -2, 3. Well, they're giving me my h and my k just in different words. Oh, and I forgot to put my x in here. So my h, I'm going to circle here. My h should be the opposite of what I think it is. So because the h is a -2, I'm going to put a +2 in here. And then my k should be the same thing, and k happens outside the function. So because it's a +3, I'm going to put a +3 here. And then it goes on to say, anything else? Write an equation that represents. So that's it. So there's no vertical stretch or shrink. They didn't talk about that. And there's no reflection. So that is our final answer for that one. All right, so let's get on to graphing. So we're going to skip number 7 and go directly to 8. And on top of the graphing, we have to find all of these things here. So we're going to talk about increasing and decreasing intervals as well. And you're going to have to circle endpoint or turning point, domain and range. And then we're also going to talk about end behavior. So all of this stuff is new, but we're going to start by graphing. If you do not have a reflection or a vertical stretch or shrink, then you can graph this quite easily by graphing the parent function and then shifting it up, down, right, or left. So as I look at this, I want to look at what are my transformations. It is a square root, so because it's a square root, I know I have an endpoint. So I'm going to circle that right now before I forget about it. And then that endpoint is the opposite of what's inside and the same as the outside. So that endpoint is going to be a +1 and a -4. That endpoint actually is going to tell you the shift. But if you think about it, the -1 on the inside of the function means that we are moving right 1, and the -4 on the outside means we are going down 4. So let's start by plotting the parent function. Mrs. Murray, do I have to graph the parent function? Yes, you do. So our parent function from the previous page started at 0, 0, and so this is something that you want to learn and remember. If not, just substitute values into the square root of x. That's your parent function. So if x is 0, y is 0, If x is 1, y is 1. Let's get that on 1, 1. And if x is 4, y is 2. And if x is 9, y is 3. I am not going to connect the points on my parent function because that's not the graph I'm graphing. I'm graphing this one here. So what I want to do is take all 4 of these points and I want to shift each one of them right 1 and down 4. So here we go. So our endpoint is going to go right 1 and down 4. So it's going to be right here. And notice that that is our endpoint here. Okay, so then our next point, 1, 1, is going to go to the right 1, down 4, so that puts it right here. And then our next one, right 1. And so then that's the next point. And then right 1. And then that's our next point. So I'm going to connect these with a green line so you can still see my pink. And that's my graph. So notice that the shape, it did not change shape at all. It just moved right 1 down 4. Right 1 down 4. Right 1 down 4. Right 1 down 4. That's it. That's all you have to do to graph these. It becomes a pain when you have this down there, but I'm going to show you how to graph those. All right, so let's talk about the domain. So remember, the domain goes from left to right. So the leftmost value for our x is here at this endpoint. If you go to the x-axis, that value is positive 1. So our domain starts at positive 1. The question is 1 included in that graph? Well, yes, because our endpoint is 1, negative 4. So our domain has to have a bracket there because 1 is included. And then, because this graph goes forever to the right, this is going to go forever up and to the right. So any direction up and to the right is going to be infinity. So our domain is from 1 to infinity. Then our range goes from low to high. So our lowest range value again starts here at this endpoint. With the endpoint, the y value is negative 4. So that is our lowest y value is negative 4. Is negative 4 included in the range? Yes, it's part of that endpoint. And then it goes up infinitely, right? So it goes to positive infinity. Next, let's talk about the end behavior. So end behavior, we have to look at the graph as, you have to look at your domain. So end behavior as x approaches. Well, our x is our domain. So you've got to approach the x from the right-hand side of the domain and from the left-hand side of the domain. So as x approaches positive infinity, so as x gets bigger and bigger and bigger, what's happening to y? It's getting bigger and bigger and bigger. You can kind of see it right here. This tells you your endpoints on the right, and this kind of tells you your end behavior on the left if you look at those. So as I look at my graph, as I approach positive infinity, what is my graph doing for the x value? The x value is getting bigger and bigger and bigger. The y value, because f of x is our y value, the y value is also getting bigger and bigger because it's going up and up and up. So as x approaches a very large number, positive infinity, because that's the right-hand part of our domain, our f of x, which is our y, is also approaching positive infinity. So again, you can see that right here. This is the right-hand behavior, the right-hand part of our domain and range. And notice that they're both here. Now, if I go to the left, x cannot approach negative infinity because it can never be over here. X is approaching the lowest value that it can be, which is positive 1. So as x approaches positive 1, your y is getting, as we get closer and closer and closer, your y is getting closer and closer until it hits negative 4. Negative 4 is our lowest y value. So really, once you find the domain and range, you found your end behavior. As x approaches, so this would be known as right-hand behavior, and this is left-hand behavior. And you could have mixed those up and put as x approaches 1, then this would have been negative 4. So I'm going to put here RH for right hand, and LH for left hand. Now, increasing intervals. For increasing and decreasing intervals, we're going to take the x-axis and split it into what part of the graph is increasing and what part of the graph is decreasing as we go from left to right. Well, the first interval that we come to, we have nothing over here. So the lowest x value that we come to is right here at 1. So as we go from a 1 value of our x and we go to the right, our y is increasing. It's getting bigger and bigger and bigger. So this is called an increasing interval from an x of 1 to positive infinity. It kind of looks like our domain, and sometimes they are the same, but in this case it is, but they're not always the same. It depends. So now, you might be inclined to put a bracket at 1, but here's the problem. Right at that endpoint, we do not know whether the graph is increasing or decreasing because it's neither. As we step off of that endpoint and go to the right, now the graph is increasing. So at the point 1, -4, the graph is not increasing or decreasing, so we have parentheses. And of course, we always have parentheses at infinity. Decreasing values, as we go from left to right, the graph never decreases. It just goes up and up and up. So on this particular graph, we have none. All right, let's look at the next graph. Let's look at 3 times the square root of 1. What do? I know for a fact that this graph is going to shift left 1 because inside the function is 1 and we want to do the opposite. So I know for a fact we're shifting left 1. I also know that this is giving us a vertical stretch of 3. Okay. Sorry, the handwriting looks terrible. But there you go. All right. So typically when I have a reflection or a vertical stretch or shrink, I'm going to use a table of values. So I'm going to do an XY table, and you're going to use your endpoint or your turning point to determine what values of x that you choose. Since I know, and let's go ahead and graph our parent function. So if I graph the parent function, it is normally at 0, 0, 1, 1, 4, 2, and 9, 3. So we don't connect that because it's not the graph we want. But I know that my graph is going to shift left 1. So it's going to go left 1. So my turning point for my x value, or my endpoint for my x value, should start here at -1. So I know that the very lowest x value that I can choose is -1. But I want to choose my x values carefully. When I substitute in -1 for x, I want to make sure that when I add 1 to it, it becomes a perfect square. For instance, let's go ahead and put in -1 plus 1. -1 plus 1 is 0. The square root of 0 is 0. Times 3 is 0. So I know that my y value is 0. The next value to the right, because I know the graph is going to go to the right, is 0. If I put 0 in here and I add 1 to it, I get 1. Well, 1's a perfect square, so I can let x be 0. Okay, so 0 plus 1 is 1. Square root of 1 is 1. Times 3 is 3. So that point will fit on my graph. Keep going to the right. This time, the next number after 0 is 1. If I put 1 in here, 1 plus 1 is 2. 2 is not a perfect square, so that's not going to work. Well, the next number is going to be, I just lost the top of my pen, is 2. All right, I have my pen back. All right, so if I choose 2, 2 plus 1 is 3. That's not a perfect square. Next number after 2 is 3. 3 plus 1 is 4. That is a perfect square. So we're going to choose 3. All right, so 3 plus 1 is 4. Square root of 4 is 2. 2 times 3 is 6. That fits on my graph. So my next number after 3 is 4. 4 plus 1 is 5. That's not a perfect square. Next number after 4 is 5. 5 plus 1 is 6. That doesn't work. Then 6. 6 plus 1 is 7. No. Then 7. 7 plus 1 is 8. No. Then 8. 8 plus 1 is 9. 9 is a perfect square. So the last one we're probably going to be able to choose is 8. So 8 plus 1 is 9. Square root of 9 is 3. And 3 times 3 is 9. So we're going to plot those points. All right. So -1, 0. And as you can see, my graph shifted only to the left, but we're also going to be getting this vertical stretch. So you're going to see the shape of our graph pull closer to the y-axis. And then I have 0, 3. See how tall it's getting now? And then I have 3, 6. And then I have 8, 9. And then I'm going to connect that, and it's an endpoint. So I have to start, and then you've got to put arrows where the graph continues infinitely. So on this one, you can see that the shape of the original parent graph has changed. It's been stretched up, and notice that it's been pulled closer to that y-axis. That's why it's called a vertical stretch. All right, so our domain. Leftmost value on the x-axis is now -1. So our domain is going to be, I think I'll do this one in red this time. So our domain is going to start at -1. Oops, and we include that. So I definitely want brackets because it's part of our domain. And then we go infinitely up and to the right. So up and to the right are going to be infinities. So right, pos infinity. Then our range, the lowest value in our range going from low to high, right here on the y-axis, that's a 0 value. So 0, and that's included. And then because it's going up and to the right, up is a y direction, so that is pos infinity. Now remember, we have an endpoint, and our endpoint you can see is at -1, +0. And we could see that originally from here. Opposite of what's inside, there's your -1. Nothing is being added or subtracted. There's your 0. Okay, so then let's look at our end behavior. And notice our end behavior we can get from these. So my left-hand behavior is the left-hand side of my domain and range. Even without looking at the graph, I can actually write that down. So my end behavior, the left-hand side of my domain as x's domain approaches -1. Your y value, so look at your leftmost y value. Oh, this is going to be left-hand behavior because I started on the left this time. My bad. So the left and the left. So we are going to go from -1 to 0. And so look what happens is I go to the left on the graph, left-hand behavior. This is the left side of my graph. As x approaches -1, because we cannot approach negative infinity, y is getting lower and lower and approaching 0. So as x approaches -1, y approaches 0. So then our right-hand behavior, so here's our right hand. So this is the right side and the right side. It should be infinity to infinity. As x approaches pos infinity, y should approach pos infinity. So let's see if that's true. As x gets bigger, approaches pos infinity, notice that y is getting bigger and bigger and bigger, higher and higher and higher. So there's your left and right hand behavior. Then increasing and decreasing intervals, we always go from left to right. So as I go from left to right, I start here, and the graph is going up. Going up is an increase. And where on the x-axis is it increasing? It starts at -1 and continues to increase, going up all the way through to pos infinity because this graph never stops. So starting at -1 on the x-axis, because we cut the x-axis and decide what's those intervals, going up until x reaches pos infinity. So from -1 to pos infinity. Now we don't put brackets because at that endpoint we don't know if it's increasing or decreasing. And then there are no decreasing intervals, so none. Okay, let's look at the last page. So on this last page, we are going to do number 10, 11, and I think there's one more. So on this one, let's look at our transformations. So we have a negative on the outside. Remember, the negative on the outside of the function means that we are going to be reflecting over the x-axis. So because we have a reflection, we are going to use an XY table. I will show you how you can do a pure reflection without doing an XY table, but a lot of you will be more comfortable doing that. But because we don't have a vertical stretch or shrink, we can do it without an XY table, but we'll get to that. All right, so then we have -2 on the inside of the function. Inside is right, left, and it's the opposite. So we're going to go right 2. And then outside affects the y. That's up, down, and it's the same. So we're going to go up 3. So I'm going to start with the fact that I have a square root. So my parent function for my square root would be at 0, 0, 1, 1, 1, 1, and then 4, 2, and then 9, 3. So that's where my parent function normally is. I am expecting this to go right 2, up 3, and then reflect over this x-axis. So if it's 3 away, you got to be 3 away on the other side. All right. So I'm going to do this in 2 different colors. So I'm going to first do my right 2 and up 3, and then I will do the reflection last. So I'm going to move everything right 2 and up 3, and then I'll reflect. So I am going to start with, I think I'll do red. So let's do red. So if I move every point right 2 and up 3, there's my first point right there. And then there's my second point. There's my third. And this one's just off the graph over here, just one off the graph. All right, so that's my right 2 and up 3. And then I'm going to highlight my x-axis, because that is your point of reference for reflecting. And I'm going to do this final color in pink. So if I want to reflect these over this x-axis, it's a mirror image. So this point go towards the x-axis is 1, 2, 3 away from the x-axis. So you have to reflect in the opposite direction, going 1, 2, 3. So you're going to plot that point right there. So here we go. So it shows up here. Then for the next point, I am 1, 2, 3, 4 away. So I have to reflect in the opposite direction. 1, 2, 3, 4. So that's where my next point will end up. Right there. And then this point is 1, 2, 3, 4, 5 away. Yeah, that's right. Yep. So 1, 2, 3, 4, 5 right there. Okay. Our last point right here is 1, 2, 3, 4, 5, 6 away. So 1, 2, 3, 4, 5, 6 right there. Okay, and so I'm going to connect that with a green dot or green line. And so that right there is my reflection. Notice, now this is going to be interesting when we get to increasing and decreasing, but this is our endpoint. So our endpoint shifted right 2 and up 3, but because it was reflected, I couldn't do my endpoint until I was ready. So notice that my endpoint is at +2, but 1, 2, 3 down, it's at -3. So our endpoint is at +2, -3. So notice that that reflection affected not my x value, but my y value, because that reflection is over the x-axis, which makes you flip up and down, which is a y value. So that makes perfect sense. All right, so let's do our domain and range. So our smallest x value for domain is here at positive 2. So we're going to start at positive 2. 2 is included, so brackets. And then we go infinitely down and to the right. So to the right infinitely is positive infinity, and right is a domain value. Now our range, you don't want to start here because you have to go low to high. Our lowest, because this goes down and down and down infinitely, there isn't a lowest on this graph. So this one's a little bit more difficult because our lowest value is all the way down here at negative infinity because it keeps going to the right and down forever. So because down is your lowest range value, it actually starts at negative infinity. And then our highest value, we're going to come up here, is right here. That's the highest point on this graph. And if you go to the y-axis, it's there at negative 3. So, negative 3. Now, normally we could look at the domain and range and do our left and right hand behavior, but the reflection kind of messes everything up. So, let's start on the left side. So let's do left hand behavior first. Okay. As x moves to the leftmost value that x can approach is right here at 2. So as x approaches 2, because that's the left-hand side of our graph, as x approaches 2, isn't y getting closer and closer to negative 3? So as x approaches 2, y is getting closer. So I'm going to follow along in this graph. As I get closer and closer to an x value of 2, notice that y is getting closer and closer to negative 3. So y approaches negative 3. So this says as x approaches 2, f of x, which is our y, approaches negative 3. As x approaches 2, and I'm going towards the left, y is approaching negative 3. All right, so then for right-hand behavior, we're going to move along the graph towards the right. So for right-hand behavior, I'm going to start here. And then as I move to the rightmost value that x can approach is positive infinity because it keeps going and going and going. So x can approach positive infinity towards the right. So as x approaches positive infinity, which is a huge number, y is getting smaller and smaller and smaller infinitely. So y is approaching negative infinity. So this is going to be hard for you at first, but try doing it that way. Walk along the line to the left and the right and see what y is doing. All right, increasing and decreasing intervals always have to go from left to right. So I'm going to start here because that's my starting point. And as I move to the right, isn't my graph going down? So from an x value, we always split for increasing and decreasing intervals, we always split the x-axis. So because my starting point starts at 2, and I'm going down, it's a decreasing interval. So I start at 2, and it decreases all the way from an x value of 2 all the way through to an x value of infinity. So the graph always is decreasing from an x value of 2 to an x value of infinity. There is no, I'm going to put none, there are no increasing intervals. Okay, let's look at 11, and then we'll have one more to do after this. So for number 11, it's a cube root. So for a cube root, we have a different parent function. So remember our parent function for that cube root, the turning point is at 0, 0. And then the cube root of a positive 1 is positive 1, so we have 1, 1. The next perfect cube was 8, so you have to go all the way to 8. Cube root of 8 is 2. All right, then the cube root of negative 1 is negative 1. And then the cube root of negative 8 is negative 2. So those are the points you should be plotting for your parent function. Again, I'm not going to connect those. I'm going to look on this one for my up, down, right, left movement because I have no vertical stretch or shrink and no reflection. So inside the function, I have a plus 3. So that means I'm going the opposite, which is left 3. So sometimes with these functions, because you don't have a lot of points to begin with, you're just going to have to estimate going to the right or the left and just do your best. Sometimes you'll be off the graph, and that's okay. So we're going to go left 3, and then the 2 on the outside of the function is a y direction, and it's exactly what we think it is, and so it's up 2. So the plus 3 means we go left 3. Outside the function is up, down, up 2. All right, so I'm going to move every point left 3 and up 2. 2, 3, and up 2 is going to put me just off here at 11, 0, negative 11, 0. And then left 3 and up 2 puts me here. And then this is going to become my turning point, left 3 and up 2. So I'm going to right now state my turning point. So it's negative 3, positive 2. I don't know if I circled that on my last one, but this is a turning point. Did I? No. So this one was an endpoint. Just to fix that. Okay, so then back up here. All right, so then let's continue. So then my next point, 1, 2, 3, up 2. And then my last point is right here. And so then I'm going to connect those with a curve, and it should be like a sideways S. And you have to have an arrow on both ends because it goes infinitely in both directions. So our end behavior is, well, let's talk about our domain and range first, and then we'll do end behavior. So our domain, if I go from the left, so this graph goes to the left forever. It's going to the left forever and down forever. So left forever is a domain, and that's negative infinity. Then it's going up and to the right forever, so that is positive infinity. Then our range, our lowest range value is going to be down here. It's going to continue to go lower and lower and lower. So our range, our lowest range value is going to be negative infinity. And our highest range value, this is going up but to the right forever, so up and right are also infinities. So the domain and range on the cube root function is always negative infinity, positive infinity. Okay, so in behavior, it should be pretty simple for this one. As x approaches, so as x approaches negative infinity, so as x is getting smaller and smaller and smaller, y is approaching negative infinity also because it's getting smaller and smaller and smaller. So as x approaches negative infinity, y is also approaching negative infinity. This is left-hand behavior because we did this to the left, negative infinity is to the left. Let's go to the right. So as x approaches positive infinity, meaning going to the right, y is going up and up and up, which is approaching positive infinity. So as x approaches positive infinity, y is approaching positive infinity. So on this one, because there's no reflection, you can see, and this is our right-hand behavior. So when there's no reflection, you can see that left hand, x approaches, y approaches. X approaches, y approaches. Right hand, x approaches, y approaches. X approaches, y approaches. When there's no reflection, you can literally just get these go to the left values for left hand, the right values for right hand. But when there's a reflection, it kind of messes things up. You have to think a little bit more. Okay, so increase and decreasing intervals. The turning point is where you kind of have to look. So here's the turning point. I'm going to kind of cut the x-axis right here at the turning point. On this graph, and it's important to note, we're always going from left to right. So our leftmost value is negative infinity on the x-axis. As we approach here, we're going up and up and up. That's an increase. Then we hit that turning point. Aren't we still going up and up and up and up and up to positive infinity? So from negative infinity to positive infinity, the graph is always increasing. So the increasing interval goes from, let me change my color, from negative infinity to positive infinity. There are no decreasing intervals. All right, last one. Let me move this. It wasn't wanting to move. All right, so our last one is another cube root function. And you're going to note that this time we have a vertical shrink because 1/2 is between 0 and 1. So we're going to have to use a table of values. So I know I have a vertical shrink, which means it's going to get closer to the x-axis of 1/2. And inside the function is a +1. That's a right-left direction. So we do the opposite of +1, which is left 1. And then outside the function is a -5, which is an up-down direction. We go the same, which is down 5. Now, you need to know where to start on your xy table. So this is a cube root function. My turning point should be in the very center. So I'm going to look to the right, left, and up, down movement for my turning point. So because my turning point appears to be at -1, -5, I'm going to start, because we're always choosing x's, I'm going to start my x at -1. So I'm going to put that kind of here in the middle of my table because I want to do a couple of values smaller than -1 and a couple of values larger than -1. Now our parent function has 5 points on it. So I want 2 points to the left and 2 points to the right. We may or may not be able to plot all these points, but we'll have to see. All right, and we want to choose, on top of that, we want to choose values that are, when added 1 to it, we get a perfect cube in here. So note that if I put -1 in here, and our perfect cubes on our parent function are +8, +1, and 0. So notice when I put this in here, -1 + 1 is 0. So there was that turning point value that we're looking for. Okay, so let's go ahead and finish that one out. So -1 + 1 is 0. Cube root of 0 is 0. Times 1/2 is still 0 minus 5. So sure enough, that turning point is going to be -1, -5. Then the point to the left of -1, so let's go ahead and plot our parent function, and then we'll start plotting. So this is our parent function. Okay. And then -8, -2. Okay, so that's our parent function. I'm not going to connect those. And then I'm going to plot this new turning point, which is -1, -5. All right, so -1, 5. Okay, so there's our turning point. So from here, I want to go to the left. So the next value to the left is -2. If I put -2 here +1, that gives me -1, which is one of those perfect cubes that I'm looking for. So great. I'm going to choose -2. Okay. So put -2 in here. -2 + 1 is -1. Cube root of -1 is -1. Half of -1 is -1/2. Well, we're going to have to plot a fraction point, which is okay. If I have a -1/2 and I add a -5 to it, I have a -5 and a half. So that wasn't fun, but okay. We just want to make sure that this value in here isn't something that we can't take the cube root of. So our next number, and if you think about this, if I went left 1, and notice that we started with this point here. When I went left 1 of this, that was at -2, right? So I'm going to go left 1 of this one, which is -8. So if I go left 1, that's -9. So if you're smart about it, you can figure out that, oh, wait, -9. If I plug in here, if I add 1, I get a -8. So -9 + 1 is -8. Cube root of -8 is -2. Half of -2 is -1. Add a -5 to that, and you have a -6. Okay. Oh, I didn't plot my -2, -5.5. So let's do the -2 and then go down 1, 2, 3, 4, 5.5, which is going to be really difficult, but I'm going to try right there. Well, it's kind of sort of there. And then -9, -6, 1, 2, 3, 4, 5, 6 is going to be right here. okay? All right, let me try this one again. And you can see that when it was shrunk a half, it went in between the two grid lines. Okay, so there we go. So we're going to see the shape on this changing. So then I want to go greater than -1. So that means I'm moving this one left 1. So if I move left 1, I'm at 0 now. So if I plug 0 in here, I do get 1. 0 plus 1 is 1. So that's a perfect cube. So I'm going to plug in 0. 0 plus 1 is 1. Cube root of 1 is 1. Half of 1 is a half. So if I have a half and a -5, they're opposite signs, so subtract. 5 minus a half is 4.5. And this is bigger, so you get a -4.5. So let's plot that. So 0 down, 1, 2, 3, 4, and ooh, a half. It's going to be real close. Oops, right there. Well, you get the idea. Okay, so then our last point is this one's going to be moved left 1. So left 1, that's a +8. Left 1 is going to be a 7. So I'm going to try 7. 7 plus 1 is 8. Cube root of 8 is 2. Half of 2 is 1. A 1 and a -5 is a -4. So to the right 7, down 4. Okay, now I can connect these with a curve, and you can see that that S has really shrunk down. It's if it hadn't been moved down 5 and we put an x-axis right through here, you can see that the curve of this is much closer to what would be the x-axis if we hadn't moved it down. All right, so our domain is still -infinity to +infinity, and so is our range. That hasn't changed. So -infinity to +infinity, -infinity to +infinity. And if we didn't have a reflection, which we didn't, these should be our left-hand behavior and these should be our right-hand behavior. So as we go to the left, as x approaches -infinity, isn't y going down and down and down, also approaching -infinity? So on the left-hand side, -infinity to -infinity. So left-hand behavior, as x approaches -infinity, y is approaching -infinity. Right-hand behavior. So as x approaches +infinity, getting bigger, y is getting bigger as well. It's approaching +infinity, and you see +infinity, +infinity. So as x approaches +infinity, y approaches +infinity. All right, let's see about our increasing and decreasing intervals. So again, we like to look at the endpoint of the turning point, and right here, that's where we would cut. The x-axis would be right there. So as I go from left to right, I'm going to follow along in this graph. So as I go from left to right, I'm getting bigger, slowly, slowly, bigger, 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 slowly, bigger, bigger, bigger. There is nowhere that I'm not increasing. From -infinity, passing that turning point to +infinity, I'm always increasing. So my increasing interval goes from -infinity to +infinity. If you had a reflection, you'd have a decreasing interval. So you have to watch that. So in this case, there's none. And that's it. So it's a lot of information, but you got this. Ask questions if you need to.